Fuel injection is the introduction of fuel in an internal combustion engine, most commonly automotive engines, by the means of an injector. All diesel engines use fuel injection by design. Petrol engines can use gasoline direct injection, where the fuel is directly delivered into the combustion chamber, or indirect injection, where the fuel is mixed with air before the intake. On petrol engines, fuel injection replaced carburators from the 1980s onward. The primary difference between carburators and fuel injection is that fuel injection atomizes the fuel through a small nozzle under high pressure, while a carburetor relies on suction created by intake air accelerated through a venturi tube to draw the fuel into the airstream. Objectives. The functional objectives for fuel injection systems can vary. All share the central task of supplying fuel to the combustion process, but it is a design decision how a particular system is optimized. There are several competing objectives such as power output, fuel efficiency, emissions performance, running on alternative fuels, reliability, drivability and smooth operation, initial cost, maintenance cost, diagnostic capability, range of environmental operation, engine tuning. Modern digital electronic fuel injection systems optimize these competing objectives more effectively and consistently than earlier fuel delivery systems. Carburetors have the potential to atomize fuel better. Benefits. Benefits of fuel injection include smoother and more consistent transient throttle response, such as during quick throttle transitions, easier cold starting, more accurate adjustment to account for extremes of ambient temperatures and changes in air pressure, more stable idling, decreased maintenance needs, and better fuel efficiency. Fuel injection also dispenses with the need for a separate mechanical choke, which on carburetor-equipped vehicles must be adjusted as the engine warms up to normal temperature. Furthermore, on spark ignition engines, fuel injection has the advantage of being able to facilitate stratified combustion which have not been possible with carburetors. It is only with the advent of multi-point fuel injection certain engine configurations such as inline 5-cylinder gasoline engines have become more feasible for mass production, as traditional carburetor arrangement with single or twin carburetors could not provide even fuel distribution between cylinders, unless a more complicated individual carburetor per cylinder is used. Fuel injection systems are also able to operate normally regardless of orientation, whereas carburetors with floats are not able to operate upside down or in zero gravity, such as encountered on airplanes. Environmental benefits. Fuel injection generally increases engine fuel efficiency. With the improved cylinder-to-cylinder fuel distribution of multi-point fuel injection, less fuel is needed for the same power output. Exhaust emissions are cleaner because the more precise and accurate fuel metering reduces the concentration of toxic combustion byproducts leaving the engine. The more consistent and predictable composition of the exhaust makes the emissions control devices such as catalytic converters more effective and easier to design. History and development. Herbert Ackroyd Stewart developed the first device with a design similar to modern fuel injection, using a jerk pump to meter out fuel oil at high pressure to an injector. This system was used on the hot bulb engine and was adapted and improved by Bosch and Clessey Cummins for use on diesel engines. Fuel injection was in widespread commercial use in diesel engines by the mid-1920s. An early use of indirect direct gasoline injection dates back to 1902, when French aviation engineer Léon Levavasseur installed it on his pioneering Antoinette 8-volt aircraft power plant, the first V8 engine of any type ever produced in any quantity. Another early use of gasoline direct injection was on the Hesselman engine invented by Swedish engineer Jonas Hesselman in 1925. Hesselman engines use the ultra-lean burn principle. Fuel is injected toward the end of the compression stroke, then ignited with a spark plug. They are often started on gasoline and then switched to diesel or kerosene. Direct fuel injection was used in notable World War II aero engines such as the Junkers Jumo 210, the Daimler-Benz DB601, the BMW 801, the Schwyz 82 FN. German direct injection petrol engines used injection systems developed by Bosch from their diesel injection systems. Later versions of the Rolls-Royce Merlin and Wright R3350 used single-point fuel injection, at the time called pressure carburetor. Due to the wartime relationship between Germany and Japan, Mitsubishi also had two radial aircraft engines utilizing fuel injection, the Mitsubishi Kinsei and the Mitsubishi Keisei. Alfa Romeo tested one of the first electronic injection systems in Alfa Romeo 6C 2500 with a La Spessa body in 1940 Miglia. The engine had 6 electrically operated injectors and were fed by a semi-high-pressure circulating fuel pump system. Development in diesel engines. All diesel engines have fuel injected into the combustion chamber. See diesel engine. Development in gasoline, petrol engines. Mechanical injection. The invention of mechanical injection for gasoline-fueled aviation engines was by the French inventor of the V8 engine configuration, Léon Levavasseur, in 1902. Levavasseur designed the original Antoinette firm series of V-firm aircraft engines, starting with the Antoinette 8 volts to be used by the aircraft. The Antoinette firm built that Levavasseur also designed, flown from 1906 to the firm's demise in 1910, with the world's first V16 engine, using Levavasseur's direct injection and producing around 100 horsepower, flying an Antoinette 7 monoplane in 1907. The first post-World War I example of direct gasoline injection was on the Hesselman engine invented by Swedish engineer Jonas Hesselman in 1925. Hesselman engines used the ultra-lean burn principle and injected the fuel in the end of the compression stroke and then ignited it with a spark plug. It was often started on gasoline and then switched over to run on diesel or kerosene. The Hesselman engine was a low-compression design constructed to run on heavy fuel oils. Direct gasoline injection was applied during the Second World War to almost all higher-output production aircraft power plants made in Germany, the Soviet Union and the USA. Immediately following the war, hot rodder Stuart Hilborn started to offer mechanical injection for race cars, salt cars, and midget races. Well known and easily distinguishable because of the prominent velocity stacks projecting upwards from the engines on which they were used. The first automotive direct injection system used to run on gasoline was developed by Bosch, and was introduced by Goliath for the Goliath GP700 automobile, and Gartbrod in 1952. This was basically a high-pressure diesel direct injection pump with an intake throttle valve. This system used a normal gasoline fuel pump to provide fuel to a mechanically driven injection pump. which had separate plunges per injector to deliver a very high injection pressure directly into the combustion chamber. The 1954 Mercedes-Benz W196 Formula One racing car engine used Bosch direct injection derived from wartime aircraft engines. Following this racetrack success, the 1955 Mercedes-Benz 300 SL, the first production sports car to use fuel injection, used direct injection. The 1955 Mercedes-Benz 300 SLR, in which Stirling Moss drove to victory in the 1955 Mille and Pierre Lovig crashed and died in the 1955 Le Mans disaster, had an engine developed from the W196 engine. The Bosch fuel injectors were placed into the bores on the cylinder wall used by the spark plugs in other Mercedes-Benz six-cylinder engines. Later, more mainstream applications of fuel injection favored the less expensive indirect injection methods. Chevrolet introduced a mechanical fuel injection option, made by General Motors Rochester Products Division, for its 283 V8 engine in 1956. This system directed the inducted engine air across a spoon-shaped plunger that moved in proportion to the air volume. The plunger connected to the fuel metering system that mechanically dispensed fuel to the cylinders via distribution tubes. This system was not a pulse or intermittent injection, but rather a constant flow system, metering fuel to all cylinders simultaneously from a central spider of injection lines. The fuel meter adjusted the amount of flow according to engine speed and load, and included a fuel reservoir, which was similar to a carburetor's float chamber, with its own high-pressure fuel pump driven by a cable from the distributor to the fuel meter. The system supplied the necessary pressure for injection. This was at port injection, where the injectors are located in the intake manifold, very near the intake valve. In 1956, Lucas developed its injection system, which was first used for Jaguar racing cars at Le Mans. The system was subsequently adopted very successfully in Formula One racing, securing championships by Cooper, BRM, Lotus, Brabham, Matra, and Tyrrell in the years 1959 through 1973. While the racing systems used a simple fuel cam for metering, a more sophisticated Mk2 vacuum-based shuttle metering was developed for production cars. This mechanical system was used by some Maserati, Aston Martin, and Triumph models between 1963 and 1975. During the 1960s, other mechanical injection systems such as Hilborn were occasionally used on modified American V8 engines in various racing applications such as drag racing, oval racing, and road racing. These racing-derived systems were not suitable for everyday street use, having no provisions for low-speed metering, or often none even for starting. However, they were a favorite in the aforementioned competition trials, in which essentially wide-open throttle operation was prevalent. Constant flow injection systems continue to be used at the highest levels of drag racing, where full throttle, high RPM performance is key. In 1967, one of the first Japanese-designed cars to use mechanical fuel injection was the Daihatsu Campagna. Another mechanical system, made by Bosch called Jetronic, but injecting the fuel into the port above the intake valve, was used by several European car makers, particularly Porsche from 1969 until 1973 in the 911 production range and until 1975 on the Carrera 3.0 in Europe. Porsche continued using this system on its racing cars into the late 70s and early 80s. Porsche racing variants such as the 911 RSR 2.7 and AMP 3.0, 904 6, 906, 907, 908, 910, 917, and 935 all used Bosch Kugelfischer-built variants of injection. The early Bosch Jetronic systems were also used by Audi, Volvo, BMW, Volkswagen, and many others. The Kugelfischer system was also used by the BMW 2000, 2002T and some versions of the Peugeot 404, 504 and Lancia Flavia. A system similar to the Bosch inline mechanical pump was built by Spiker for Alfa Romeo, used on the Alfa Romeo Montreal and on U.S. markets 1750 and 2000 models from 1969 to 1981. This was designed to meet the U.S. emission requirements with no loss in performance, and it also reduced fuel consumption. Electronic injection. The first commercial electronic fuel injection system was Electrojector, developed by the Bendix Corporation and was offered by American Motors Corporation in 1957. The Rambler Rebel showcased AMC's new 327 cu in engine. The Electrojector was an option and rated at 288 bhp. The EFI produced peak torque 500 revolutions per minute lower than the equivalent carbureted engine. The Rebel owner's manual described the design and operation of the new system. The cost of the EFI option was $395 and it was available on 15 June 1957. Electrojector's teething problems meant only pre-production cars were so equipped, thus very few cars so equipped were ever sold and none were made available to the public. The EFI system in the Rambler ran fine in warm weather, but suffered hard starting in cooler temperatures. Chrysler offered Electrojector on the 1958 Chrysler 300D, DeSoto Adventurer, Dodge D500, and Plymouth Fury, arguably the first series production cars equipped with an EFI system. It was jointly engineered by Chrysler and Bendix. The earlier electronic components were not equal to the rigors of underhood service, however, and were too slow to keep up with the demands of on-the-fly engine control. Most of the 35 vehicles originally so equipped were field retrofitted with 4-barrel carburetors. The Electrojector patents were subsequently sold to Bosch. Bosch developed an electronic fuel injection system called Jetronic, which was first used on the VW 1600 teraliters E in 1967. This was a speed-density system, using engine speed and intake manifold air density to calculate air mass, flow rate and thus fuel requirements. This system was adopted by VW, Mercedes-Benz, Porsche, Citroën, Saab, and Volvo. Lucas licensed the system for production in Jaguar cars, initially in Jetronic form before switching to L-Jetronic in 1978 on the XK6 engine. Bosch superseded the Jetronic system with the K-Jetronic and L-Jetronic systems for 1974, though some cars continued using Jetronic for the following several years. In 1970, the Isuzu 117 Coupe was introduced with a Bosch-supplied Jetronic fuel-injected engine sold only in Japan. In 1984, Rover fitted Lucas electronic fuel injection, which was based on some L-Jetronic patents, to the S-Series engine as used in the 200 model. In Japan, the Toyota Celica used electronic multi-port fuel injection in the optional 18RE engine in January 1974. Nissan offered electronic multi-port fuel injection in 1975 with the Bosch L-Jetronic system used in the Nissan L280 engine and installed in the Nissan Fairlady Z, Nissan Cedric, and the Nissan Gloria. Nissan also installed multi-point fuel injection in the Nissan Y44 V8 engine in the Nissan President. Toyota soon followed with the same technology in 1978 on the 4ME engine installed in the Toyota Crown, the Toyota Supra and the Toyota Mark II. In the 1980s, the Isuzu Piazza and the Mitsubishi Starion added fuel injection as standard equipment. Developed separately with both companies' history of diesel-powered engines. 1981 saw Mazda offer fuel injection in the Mazda Luce with the Mazda Fe engine, and, in 1983, Subaru offered fuel injection in the Subaru EA81 engine installed in the Subaru Leon. Honda followed in 1984 with their own system, called PGM-Fi, in the Honda Accord, and the Honda Vigor using the Honda ES3 engine. The limited production Chevrolet Cosworth Vigor was introduced in March 1975 using a Bendix EFI system with pulse-time manifold injection, 4 injector valves, an electronic control unit, 5 independent sensors, and 2 fuel pumps. The EFI system was developed to satisfy stringent emission control requirements and market demands for a technologically advanced responsive vehicle. 5,000 hand-built Cosworth Vigor engines were produced, but only 3,508 cars were sold through 1976. The Cadillacs of IL was introduced in 1975 with an EFI system made by Bendix and modeled very closely on Bosch's D-Jetronic. L-Jetronic first appeared on the 1974 Porsche 914, and uses a mechanical airflow meter that produces a signal that is proportional to air volume. This approach required additional sensors to measure the atmospheric pressure and temperature, to ultimately calculate air mass. L-Jetronic was widely adopted on European cars of that period, and a few Japanese models a short time later. In 1980, Motorola introduced the first electronic engine control unit, the EEC3. Its integrated control of engine functions is now the standard approach for fuel injection systems. The Motorola technology was installed in Ford North American products. Elimination of carburetors. In the 1970s and 1980s in the U.S. and Japan, the respective federal governments imposed increasingly strict exhaust emission regulations. During that time period, the vast majority of gasoline-fueled automobile and light truck engines did not use fuel injection. To comply with the new regulations, automobile manufacturers often made extensive and complex modifications to the engine carburetor. While a simple carburetor system is cheaper to manufacture than a fuel injection system, the more complex carburetor systems installed on many engines in the 1970s were much more costly than the earlier simple carburetors. To more easily comply with emissions regulations, automobile manufacturers began installing fuel injection systems in more gasoline engines during the late 1970s. Open-loop fuel injection systems had already improved cylinder-to-cylinder fuel distribution and engine operation over a wide temperature range, but did not offer further scope to sufficient control fuel-air mixtures in order to further reduce exhaust emissions. Later closed-loop fuel injection systems improved the air-fuel mixture control with an exhaust gas oxygen sensor. Although not part of the injection control, a catalytic converter further reduces exhaust emissions. Fuel injection was phased in through the latter 1970s and 80s at an accelerating rate, with the German, French, and U.S. markets leading and the UK and Commonwealth markets lagging somewhat. Since the early 1990s, almost all gasoline passenger cars sold in first world markets are equipped with electronic fuel injection. The carburetor remains in use in developing countries where vehicles vehicle emissions are unregulated and diagnostic and repair infrastructure is sparse. Fuel injection is gradually replacing carburators in these nations too, as they adopt emission regulations conceptually similar to those in force in Europe, Japan, Australia, and North America. Many motorcycles still utilize carbureted engines, though all current high-performance designs have switched to EFI. NASCAR finally replaced carburetors with fuel injection, starting at the beginning of the 2012 NASCAR Sprint Cup Series season. System components. System overview. The process of determining the necessary amount of fuel and its delivery into the engine are known as fuel metering. Early injection systems used mechanical methods to meter fuel, while nearly all modern systems use electronic metering, determining how much fuel to supply. The primary factor used in determining the amount of fuel required by the engine is the amount of air that is being taken in by the engine for use in combustion. Modern systems use a mass airflow sensor to send this information to the engine control unit. Data representing the amount of power output desired by the driver is also used by the engine control unit in calculating the amount of fuel required. A throttle position sensor provides this information. Other engine sensors used in EFI systems include a coolant temperature sensor, a camshaft, a crankshaft position sensor, and an oxygen sensor, which is installed in the exhaust system so that it can be used to determine how well the fuel has been combusted, therefore allowing closed-loop operation. Supplying the fuel to the engine. Fuel is transported from the fuel tank and pressurized using fuel pump. Maintaining the correct fuel pressure is done by a fuel pressure regulator. Often a fuel rail is used to divide the fuel supply into the required number of cylinders. The fuel injector injects liquid fuel into the intake air. Unlike carburetor-based systems, where the float chamber provides a reservoir, fuel-injected systems depend on an uninterrupted flow of fuel. To avoid fuel starvation when subject to lateral G-forces, vehicles are often provided by an anti-surge vessel, usually integrated in the fuel tank, but sometimes as a separate, small anti-surge tank. EFI gasoline engine components. These examples specifically apply to a modern EFI gasoline engine. Parallels to fuels other than gasoline can be made, but only conceptually. Injectors, fuel pump, fuel pressure regulator, engine control unit, wiring harness, various sensors, crank cam position, Hall effect sensor, airflow MAF sensor. Sometimes this is inferred with a MAP sensor. Exhaust gas oxygen sensor, ego sensor, UEGO sensor, engine control unit. The engine control unit is central to an EFI system. The ECU interprets data from input sensors to, among other tasks, calculate the appropriate amount of fuel to inject. Fuel injector. When signaled by the engine control unit, the fuel injector opens and sprays the pressurized fuel into the engine. The duration that the injector is open is proportional to the amount of fuel delivered. Depending on the system design, the timing of when injector opens is either relative each individual cylinder, or injectors for multiple cylinders may be signaled to open at the same time. Target air-fuel ratios. The relative proportions of air and fuel vary according to the type of fuel used and the performance requirements. See air-fuel ratio, stoichiometry, and combustion.